I'm Professor Karen Hensler from the University of Ottawa, and welcome to our November Answer Create Top Seminar. So it's Professor Joshua Pierce, who is the Thompson Chair in Innovation at the Ivey Business School and the Department of Electrical and Computer Engineering at Western University. He started there not long ago, and he's been at a number of universities before. And I'm just going to start with the ending of his bio. He's published a lot in many fields in both solar and also on sort of the maker movement. And I think he's going to be talking about both today. And I've read many of his papers over the years, always inspiring. He runs a brand new lab at Western, which is called the Free Appropriate Sustainability Technology Lab. And I hope he's going to talk a little bit about all the great installations that he's building there. So today's title is Leveraging Open Hardware to Slash the Cost of Solar PV Research. So let's welcome Professor Joshua Pierce.
It's great to be here. And because many of you are what I was or what I started out to be, a photovoltaic researcher, even those of you that don't touch photovoltaics, I'm hoping that what we go through today will be useful in your own research. So we're just not talking about solar. So this picture kind of outlines what this talk is really all about. And so I had a student that joined my group that wanted to work on battery research, which is something that we've never done before. And immediately she started asking me for things that we didn't have. And so her project is to take spent solar cells that are no longer good for making solar electricity, taking the silicon from them and converting them into batteries. And so the first thing that we needed was a ball mill in order to smash the silicon down into small particulate sizes so that then put it into a 3D printer to make the cathodes for the project. And so rather than purchasing one off the shelf, we build our own. And the advantage of ours is that it's better than everything that you can buy in the market. It's completely open source. You can fabricate it yourself. It's solar powered, of course, because everything we do basically is solar powered. And so you can use it off grid or on grid, which would make it possible for anybody, no matter where they happen to be in the world, to replicate this work. All of our research now follows this paradigm where we make the things that we need so that we have complete control over them, so that we can do things that others can't. We share and we get partners. And so the outline of what I'm going to talk to you today about is first introduce you a little bit to open source, and I know many of you are familiar already. Talk about how I came to the world of open source as a solar cell researcher. Talk about how you can use open source tools to do your own research, specifically in solar, but it really works for everything. And then what our group is up to now, why you want to publish open hardware in general, because all of us really do create it if you're doing anything experimental. And then finally, but not last but not least, I'm going to give you a bunch of cool stuff. So hopefully you'll stick around to get some of that. So first, why open source? The reason I use open source as a means of innovating is that it is superior. You get faster innovation. There is zero question about that now. The software industry has shown us that for decades. If you use the internet, you use open source software, even if you don't know. The next talk will be on Blender, which is an open source, extremely powerful CGI package. Why is it so good? Thousands of people all over the world collaborated to make it good. If anybody sees something wrong with it, they can fix it. And when you have lots of people doing that, you end up with better things. And so kind of classic examples of open source would be Linux, which is more or less runs the whole internet, Android, which has taken over the smartphone market. If you have a supercomputer, like the very valuable computers you have here that I'm not allowed to know where they live, they're running Linux. I know they are, because all supercomputers in the whole world run it now, because it's flagrantly better, it's superior. Wikipedia, better than Encyclopedia Britannica. And not only does it use open source development of the definitions of things, it's running open source software, Wikimedia, on the back end. So open source as a technical means of innovation, no matter what it is, has already proven itself. It's faster, it makes better technology, and everybody can value or can harvest the value from it, like all of us that have used Wikipedia have done. Now, how did I get into open source stuff? Now, back when I was in college, I ran a Linux server with my friends because we did not email yet, but that I didn't even really know what I was doing then. I was just using it because it was there. I really got into open source when I was working with MIT on the One Laptop per Child project. And this was a brilliant idea at the time. They're making laptops for $100. And the idea was, if you could get these distributed to the developing world, you could put anything on them, you could have top-of-the-line education for everybody. The one thing they found is that people that really need it don't have electricity to run their laptops. And so my team was developing a solar power solution that would be integrated into the back of the laptop, and you have a solar powered laptop, and then it would work pretty much everywhere. And I was finally at a university, at Queen's University, and had a rapid prototype. I'm so very excited. Anything you could think of, you could fabricate in three-dimensional space and you could hold it in your hand. Like for an engineer, that's like Christmas, like awesome. So of course we did it for our little laptop project. The problem is the plastic that came out of that machine was $65. Now the laptop was 100, and I know $100 laptop doesn't seem like a big deal now, but back then that was a huge amount of money. And $65, you're killing us. The solar cells and the electronics were way less than that. This is plastic that should basically be free. So I got on the internet and decided there's got to be some way to do this. Like it just doesn't make sense. And I came across this RepRap project. And so RepRap stands for Self-Replicating Rapid Prototyping. And so Adrian Boyer, the guy on the left, is a professor or was a professor in the UK at Bath University. And he had access to a 3D printer just like I did. And he used it to make a 3D printer, but then made the parts for the next 3D printer. And I saw that as like, this is going to be giant. There's no question in my mind. And I was not the only person that thought this. And you could start to see the evolution. So because it was open source, every time somebody used it and found something wrong with it, and these initial ones were just basically garbage. You had to like see the potential in them. They had to, because of the license, share their improvements back with the original creator and with the rest of the world under the same license. So that's the true secret of open source software. You just can't use it and you can go sell it and you can even make money off of it. Like Red Hat has sold for billions of dollars. All of their products you could download, you can burn CDs of them and go sell them on the street corner. The reason they made their money is they built a business model around an open source product that was much, much better than everything else at the time. And so they did the same thing. So everybody that used the RepRap that found something wrong with it were obligated to reshare their improvements. And so they got much, much better, much faster. And so my group was no different. So on the first image with Yvonne and Rob, we were trying to use a 3D printer to be manufactured in order to make the parts for our little solar powered laptop. That printer was so bad, the very first time we used it, it broke. And so I had two students holding the corner of it together, printing out replacements to fix the part that had broken. That was our first print. Then we started to get better. So by the time we got to Brennan, that printer took two students an entire summer to build. This printer took one student a semester to build. And it was very clear, at least to me, that you could start to use these to do real things. And this also introduced this idea of using the open source mentality to do research. So we built this printer and we wanted to test to see if it was mechanically, as good as the multi-$100,000 ones down the hall. This cost, well under $1,000 to build. And because we, to get enough replications to make it statistically relevant, we needed a lot more printed specimens. Well, it took more than a half an hour per specimen. Every AST thing, you needed 10 specimens. Like this was going to take forever to do. So I posted on the internet. I said, we're going to do mechanical tests on 3D printed parts. If you have one of these RepRap 3D printers, follow my kind of like little page layout of how to do this, download the files, use them to print out your thing, send them to me. I'll test them for you, tell you how big your printer is, and then I'll add it to the conglomeration of everybody else. And this is the beauty. Random people on the internet, mostly working from their garages or their basements, high school kids, people in the industry doing it as hobbies, were able to outproduce using the same materials, stronger specimens than Stratasys that had a 20-year head start. And it's not like Stratasys is a bad company. They had good 3D printers, a good 3D printer company. Their printers, the cheapest one at the time was 20 grand. Usually it was like hundreds of thousands of dollars. We could beat them with a $1,000 printer using their own stuff. The open source community also started printing with PLA, polylactic acid. Why? Because it was easier to print with. It also happened to be stronger. So the random person on the internet was able to make stronger parts out of plastic than the most experienced company at the time, and we were crushing them. Now, when things started to get really interesting is this third version down here. So this was around 2012, where I was working as a TV researcher, like many of you. And one of the things that we do to test the solar cells, we put different colored light on it or different intensity of light according to what the solar cell does. And one of the things that I used in my lab was automatic filter field changer. This is so grad students don't have to sit there for like this for hours. Mine broke. Immediately went online, tried to find one. $2,500. And that hurts, but that's not that good. But it was a 5-month lead time. It's like, and I was the only two people that needed them in the whole North America. So it was right in the beginning of the summer, right before we were going to get going, and we got stuck. So what I did is I hired a high school student to use a discarded computer because I was for kind of early career research at that point. I didn't have a lot of money. So the computers that were not good enough for the computer labs, I took, threw on Linux, threw on OpenSCAD, which is a script-based CAD package, and taught a high school student how to do it in like half an hour. He made me the best filter wheel change on the market. It was exactly what I wanted. And we had complete control over everything about it. You could change the size of it, and it was all parametric. So if you need a filter wheel out there, you can just download this, and you can immediately have the best filter wheel changer on the market. We printed it out on one of these. Now you see the 3D printers are getting less and less parts. We're still using like old computer power supplies that we ripped out of one of the other computers. So we were basically building this from junk and getting high-end technical capabilities. And so I went in full bore at this point. So half of my research stayed in photovoltaics. The other half started going to 3D printing. So I taught a 3D printing class where everybody had to make a 3D printer from scratch. And you notice these 3D printers look nothing like the ones before. Why? Because some German had taken a RepRap project, seen that you could actually make it go a lot faster with a pick and place robot, made an open source pick and place robot that became the new RepRap engine. And then from then, my group started to, it was faster. It was just, we started to do all different kinds of things. I also wrote the open source lab, which is where I started to apply everything that we were doing following this digital replication method. So that if I was going to use a tool, I would to share the tool so that other people could copy what I did. And that's proven very successful for my career because it's very, very easy to copy me. So lots of people do. And then because they're following the same train of thought, they're obligated to share with me, I can move faster myself. And so our research tends to go really, really quick. So by the time we got to this bottom one, we were able to build one of these printers in under 8 hours. And that's like a random person off the street, not one of my good students, for under $500. And so we were annihilating what Stratasys could do using stuff that you could get at your local wood shop. As part of that class, if you were grad students, it was undergrad and grad listed. Undergrads just had to build a printer and do some progressively more detailed design experiments. The grad students had to make a material change to the printer to get better. And so Jeff made the first, to the best of my knowledge, solar-powered Delta robot. And so the idea here is you would have a duffel bag. You'd go anywhere you could get a duffel bag, like for the airport, random country. You could start manufacturing things, and you could manufacture everything that we do in the lab at that location. So he is now the director of research in Zimbabwe at his university. He actually became a full professor before I did, which is pretty good. And this was the beginning of this idea you could distribute manufacturing. So all throughout history at this point, so it's the Industrial Revolution. If you wanted to make something and have everybody buy it, smart money said that you build a big plant, you get your IP locked down on it, and you manufacture a gazillion of them and you sell them all over. And the reason you would do that is even if I include the cost of the labor. And some people that make a lot of money with that is very, very nice. So we started to use the 3D printers to go beyond 3D printing. And so we made syringe pumps, attached them to the top of the printer. And rather than have the head move at the bottom, we made a stage printer. So we moved the stage and the top head again can sit at the top. And so we can start to do anything that you could push through a syringe, like a ceramic. You could print that. You could put a mill on the top of it and start to mill out your own boards. Now, if you look at these two images, the one is ours, and the other one is a professional PCB mill. You'll notice that the professional PCB mill is slightly better, but it doesn't matter for 99% of the cases. You're just making conventional, normal, one-sided boards. We're more than good enough, and that is built on the same $500 printer that you had doing all the rest of your stuff. So the way free and open source hardware works for scientists kind of demonstrated in this cartoon. So the first scientist, she needs a test tube, and so she needs it for herself. She's going to digitally fabricate it. So she CADs it up, and she takes one small extra step. She was going to do all that work anyway. Instead of stopping there and making her own test tube, she uploads it with an open source license that forces everybody else that uses it from then on out to reshare their inventions. And so the second scientist builds a test tube stand, which is slightly useful. Third one makes a centrifuge. But now the first scientist can use her 3D printer that she made the original test tube for and make all the other stuff. It didn't cost her anything other than a little bit of material cost, a little bit of electricity, and the time that it takes you to download something to print it is basically the same time that it takes you to order something on Amazon. Only you get it right then and you get exactly what you want, especially if it's parametric. And so we started doing this for all of our stuff. So for mixing chemicals, we made it that way. If we're centrifuging, we made it that way. And so all of our tools are as much 3D printed and digitally manufacturable as possible, including the electronics for them. And every time it would be the standard costs. So something that would be really be very helpful to many people in this room would be optics. So if you do optics experiments of any kind, lasers, PV, whatever, you know that it's very, very expensive. Stupid little lens holder. It's $50 easily. At the university I was working at, we were blessed maybe with a bunch of old desks that were faux wood. They were metal. And so came up with the idea of starting to use magnets to hold the things down so we built optics tables for the desks that we already had. And so this ended up being more flexible and better than building an optics table. But if you need something of like optics table quality, if you buy optical rail, it's around $380 per meter. Open beam, which is just as good, it's $12 per meter. And then you can use the open source parametric files that we have to connect anything that you want to it, no matter what it is. We did a whole big bunch of things, like our whole lab was run off of it, 97 to 99% savings on every single item. And of course, you're getting exactly like that. So since then, we've gotten more and more sophisticated. So if you're doing micro manipulators, there's 3 different kinds here. The middle one in orange is if you've just been doing something very gross. If you're starting to get down to the sub-millimeter, you need the bottom left one. If you want to do like your crazy micron stuff, it's the one in the middle. We made a optical gimbal system so that we could test optical coatings for our solar cells and other test angles. During the pandemic, like many of you, you probably got frustrated because we're building electronics. Chips you wanted were missing. And nothing is more irritating than having an open source product at one university that you knew and then not being able to make it at the new university you just went to. And you could buy the small little surface mounts. Has anybody in this room ever soldered a surface mount? Yes. And do you like it? It's terrible. And even if you're really good, it takes forever. And so what we did was a 3D printed converter that would take surface mounts on the inside and you just plug into your kind of normal breadboard. It took, I said, 50 iterations before we got this right. But now we did it. It's done. So if you have a surface mount and want to convert it into something you can prototype with quickly, you just download those, print out as many as you want. You can customize them to whatever chip you might want, and you have access to far more, say, Digit's repository than you can normal. I got this fantastic tour of the clean room here. One of the things that I did when I was in sabbatical in Finland was to try to bring the open source stuff that we're doing 3D printing into the clean room. And so we did all these studies that are not the most, nobody's going to win the Nobel Prize for this, but we proved that it doesn't make dust. So now you can print something in the clean room so you don't have to worry about dust. So if you need to do custom things like a custom wafer holder because you're trying to get more experiments out per wafer, that's no trouble. Then we also did the chemical work as well. And so this very busy chart is showing all of the commercial 3D printed plastics at the time and their chemical compatibility with different things you'd be using in a clean room. On the bottom line is no matter what you're doing, no matter how crazy the chemical bath is that you're using, you can make custom things, which means that you can start to do experiments that you wouldn't otherwise be able to do. But let's say that none of this is good enough. Also should know that by doing ALD coating, we're in the studios, you guys are going to get your own ALD tool next year. You can then coat the plastic with the ALD. And so we were doing high vacuum work with it, which means you can make high vacuum chambers or equipment that goes into high vacuum environments out of plastic printed on a $1,000 printer. So that is a way that I think more so than anything else that I'm doing, at least with many of the groups here, you might be able to get some really good mileage out of these concepts. Now, for us, we started to branch out a little bit and to do open hardware for other researchers and then bring it back into our own group. So a biologist wanted us an open source syringe pump, so we made one for her, and then we used it for our own work, and we started using it for fluid handling. And then when I was in Finland, we did a feedback syringe, and so now you can start to do material science on things that can be extruded out of a syringe, like slot dies. So if you go and purchase a slot die, just a little handheld one, and get it machined, it's like four grand, and it's a pretty hardcore machine. 3D printing, it's trivial, and also costs a lot. And so again, parametric slot die system, messed around with it, got down to 17 nanometer thin films, which is starting to get to the realm of like, that's actually interesting to me. We can use this as an actual semiconductor processing system that is an old 3D printer that we just put on a slot die syringe pump on a printer that we no longer use for plastic 3D printing because it wasn't good enough anymore. It's served its lifetime. We're now using much better printers. We did something similar with a 4-part probe. You guys have a mapping program over here?
Not a mapping one, yeah.
So they're very expensive. Like let's say Intel have one. I have one. It's an old 3D printer. It's that's what we did. We ever wanted to do beautiful things. And we have the open source electronics and the software for it. So if you ever want to take your stationary bookmark code and start to do big areas, this is now available for the taking. Now, overall, open source software basically rules the roost. It's the industry, basically everybody uses it. You've heard a lot about AI. If you drill down into what's running all of the AI systems, it's all open source on the bottom layer. TensorFlow, all that stuff is all open source. It's completely saturated the academic realm, and you can kind of see that this is a log scale of Google Scholar citations for open source on the top and open hardware or open source software on the top and open hardware on the bottom. Open hardware is also growing by leaps and bounds, but it's roughly 15 years behind. And so you can say in 15 years, you're probably going to be able to download any type of hardware you have interest in. Why would that interest you as a solar cell researcher? It's because it will cost you less money. So I did a review in 2020 of all of the open hardware that has been published. And the bottom line is it saves 87% off of the commercial equivalent. If you use open source electronics like an Arduino and 3D print it, that jumps up to 94%. And there's lots and lots of examples that go way over 99%. As an example, let's consider the syringe pump. And this also explains how if you're a young faculty member, you can use the concept of open source to get grant money. So you're going to go, let's say, to EdCirc, and you want to develop a new tool. You could have them, or you want to develop a new process. So you could purchase the commercial stuff from, vendor, and that's great, and you could do that process. Or you could ask for money to build the tool to do the process. So in the case of the syringe pump, I knew exactly how much that cost. It was $30,000. That was the cost of the time for the people to do it and the equipment, and it included a 15% overhead from my former university. The first month it had been downloaded 1,000 times, which means that even the cheapest syringe pump that was replacing out the market was $168,000. If you went up to the more expensive, like double syringe pump that's shown there, that's $2.5 million. Since then, that syringe pump plan has been downloaded over 10,000 times. It's been modified by many different people to make it compatible with different sources of electronics. It's been used for all different kinds of applications. That system has made the science funder a return on investment at a minimum of 750%, if not more than 12,000. And that's just the ones I know of, because you can download it once and make as many copies as you like. And you may say, well, isn't some people don't think download it and not use it? Possibly, but that's a lot of effort. That's a lot of components that you're downloading. Just most people would probably make one. At least that's my theory. We do lots of other open source things that I think overlap at least a little bit with what's going on here in Ottawa of a DC powered nanogrid. And so the idea here is if you're off grid for whatever reason, whether it's a parking lot that doesn't have, you don't want to dig it up to run cables to, or you're in the middle of the developing world, or you're really far north and you're on a microgrid anyway, run on diesel fuel, instead of converting everything to AC, why not just stick with DC? Our laptops are DC. We make electricity, convert it into AC, convert it again back to DC. Why don't we just skip all the converting and run everything off of DC if we're starting the solar anyway? And so we created this DC nanogrid. It's not good enough to be a microgrid. It's tiny. The idea is that we can choose any voltage, so you can use it for any system that you might need. And we've been doing a lot of work with this idea of going someplace that doesn't have anything and seeing what we can do there. So this is a DC powered, photovoltaic powered humanitarian 3D printer. So it's a little bit more rugged than the ones that we build for our labs, with the idea that you could run it at the back of a truck. This is Ben. So of all my students, it's definitely the most adventuresome. So this is South Sudan during the war, doing 3D printing outside the solar panels. And this was one of the coolest things that he made, was a club foot brace. And so that's, of course, better than all the club foot braces you can buy currently. It's completely 3D printable except for a couple nuts and bolts. Can be manufactured anywhere, can be sized for any type of little child, and can grow as they age. The problem's not fixed by then. And it can be manufactured by one of these 3D printers, literally anywhere. We also do a lot of snow stuff. I know Ottawa is also interested in some of these things. So there's lots of collaborative opportunities. I would say our group's contributions to this area, we've been trying to figure out the snow problem for years. Two things that I know. One is if I'm going to study snow for photovoltaics, when I build it, it will be snowing. It doesn't matter how much I plan ahead of time, the students always end up freezing their butts off. And it's just terrible. Like, just how big those snowflakes are, like, it's insanity. So, I've done a couple different ones of these, some in Canada and some in north Michigan. I have not been able to crack the nut yet. I've used snow losses. The best we've been able to do is with the bifacials, that it massively increases the losses. I do, however, have a way that you can put wax on a piece of glass that gets snow to stick to it at 90 degrees. If you know of an application, happy to help. But where we could possibly contribute is we've been doing a lot of work on developing the software to be open source, of course, to be able to monitor snow losses. So we've adapted some of the things we've been doing with 3D printing or monitoring 3D printers in real time, trying to fix them and using the same techniques to monitor snow losses on IP. If you do outdoor photovoltaic work, that's this kind of building your own scientific equipment is just not for the indoors, it's also for the outdoors. That little script there, which is only a couple lines of code, makes it possible to build a shadow band for any pyranometer or any model or all of them. If you do the code right once, no one else needs to mess with it ever again. They just put in the first couple variables in the OpenSCAD script will allow you to make anything for any of the different tools. We do a lot of 3D printed stuff for the outdoors, so radiation shields, again, slashing the cost down to nothing, very easy to do. So you can put electronics. And if you do the shield, well, why not do the whole weather station? And so for pennies on the dollar, you can start to think about putting weather stations, feasibility studies anywhere in the world that might be interested in, and all of that, again, is free, open source. The Wi-Fi model, if you have Wi-Fi, the site is 512, costs another $50 to get 2G. And so then you can offer it as long as it has cell phone. I haven't figured out our own network yet, but we'll get there. One of the things we talked about was the multispectral albedo. And so one of the things I'm really excited about is agrivoltaics. And if we're going to have bifacial modules associated with it, it would be nice to know what colors of lights are coming off of the ground at different locations all at the same time. And you can buy a very expensive odometer that has basically 2 pyranometers that are spectral, glorious stuff, bajillions of dollars. You have no control over what's going on anyway, or you can build a cheap way. And so what we've done is made a bunch of LEDs at various wavelengths. So we're sort of covering the whole spectrum. It's not going to be perfect, but it's good enough to get nice curves for anything that you might be going over. And then we've attached it to a little GIS module so that you can like walk over an area and then map it out in terms of color intensity and colors that you're interested in for your given array. Which brings me to agrivoltaics. So all of the work that I'm doing now, this is the area that I think PV has the greatest capacity for massive growth. So agrivoltaics is when you purposely plant crops underneath solar panels or next to them for the reason to not only get the solar electricity, but also get increased agricultural production. There have been studies all over the world at this point that have shown amazing things. The best one that I'm aware of is a pepper study in the US, 250% yield increase. Put the solar panel over the peppers, get 250% more peppers. Some of the other ones aren't quite as impressive, like Germany, there's wheat one that get 2% increase. It's still more food and way more energy. And so I did one of the early theoretical pieces of work in the US that showed that we could double the PV capacity for America if we only did lettuce. And lettuce is one of those crops that's guaranteed to grow more because the thing that you're after is the leaves. You put less sunlight on it, it tends to push more growth to the leaves, so you get more lettuce. Everybody wins. The first people win, of course, the people harvesting the crops, because now they don't have to be in the sweltering sunlight. They can be in the shade. And that's one of these like added special benefits that no one talks about when you start combining things and think about optimizing the whole system. So in the agrivoltaic case, you still get the renewable energy, you get the reduced CO2 load as not coal plants off the grid. That means decrease in temperature increases from climate change. But one of the biggest advantages of agrivoltaics is you create a little microclimate under the modules, conserves water. So you don't have to water as much, you get increased plant growth. The modules also shield the plants from too much sun, too much wind, from hail, from too much erosion, and that stops desertification. You still get the local job for doing the farming. So in the US, in particular, where I was from, kind of the middle of the US, people don't like solar as much. You got a lot of weird stuff going on in the politics of the US. And well, part of it is that rural communities feel that bringing in industrial PV systems, putting them on their land, they don't get really hardly any benefit other than maybe the landowner. And they literally started to protest. And it's actually uncomfortable. Usually you think of yourself as sort of a nice guy, trying to do some social stuff and then it's from it. It makes it feel a lot better when you're like, whoa, nobody loses their jobs here. And in fact, food prices go down and there's so much tax revenue generated from the increased income on the farm that you can do stuff like build programs and schools for your kids. That's a much more comfortable thing to talk about. It gets you away from the politics, at least in the US. I'm doing another study now where we're looking at Canadian context for this, and I'll let you know how that goes. Hopefully it comes out the same, because right now there's definitely some problems here. We're getting large scale Canadian as well. So you get local food, which is good for health, much more economic advancement. And then there's opportunities. So part of the challenge in all of North America is getting the solar electrons on the grid. When you have a government that's pro-solar, that's very easy. When you have a government that's anti-solar, it can make it almost impossible, which means that if you're going to put in an economic, even if you can generate solar electricity for less money than it costs you to buy electricity from a fossil fuel plant, it doesn't matter if you can't get grid access. And so then you've got to be slightly more creative. And so that means using the solar electricity to generate electricity for vehicles, for hydrogen production, or ammonia, or nitrogen fertilizer. And so these are kind of like the big growth areas of the future. And then one of the other ones that we're playing with is integrating PV onto the rooftops of greenhouses so that they can become kind of climate neutral food producers as well. So the agrivoltaic potential in Canada is awesome. So we did this little study where we looked at two types of PV systems, a vertical PV system and a single axis tracker. And the reason these are so interesting in Canada is that it allows you to use the exact same farming equipment that you do now. All you do is space the rows apart for the width of the farming equipment, whatever it happens to be. 4% of the agricultural land in Canada, kind of demarcated by the colors on the map, can provide all of our electrical needs with vertical. 3% can do it with single axis trackers. If our goal wasn't to make it completely solar power grid, let's just say we wanted to get rid of fossil fuels, we need 1% of the agricultural land area. And remember, that means more food too. I don't know that that would lead to lower grocery store bills, but we can all pretty people. So to kind of push this forward, we founded Agrivoltaics Canada. All of you can become members if you want to. We had the first agrivoltaics conference in Canada last year. In December, we're having another one on December 11th. Again, all of you are invited. If you go to agrivoltaicscanada.ca, you can sign up to come. It's a consortium between solar researchers, solar developers, farmers, policy makers, people in the government, people that see the opportunity for this. So our friends, and most of you at NREL certainly know this, in the US, they take agrivoltaics seriously. There's multi-million-dollar grants for it. There's lots and lots of things going on. In Canada, we need to do this, possibly by forming a partnership between Ottawa and Western to really start to kill this. Overall, by 2030, they're expecting to be about $9 billion. And that's like, we haven't even scratched the surface yet. Like there's hardly any agrivoltaics anywhere really. To push this forward, I'm creating what I affectionately call the Disneyland of agrivoltaics at my University of Western. So this is a farm that Western owns that they use it for biological research. So they have like bird studies and insect studies and stuff like that going on. And I have gained access to some of it to play agrivoltaic wonderland. So we're doing FPV on the lake. We have a bunch of man-made like little mini ponds that we do the initial experiments on. We're doing PV integrated into fencing, into barns, single axis tracking, fixed tilt, variable tilt. We're also developing a whole big bunch of our own racks for different types of crops and greenhouses. So this is going to be pretty fantastic. Right now, it's like medium scale fantastic. We've got a couple things out. The big contract for the next 115 kilowatts is still pending. But we have the RFP has gone through, the vendor's been selected. We're just negotiating the final installs to get these things going. And the idea of each of those lines represents about 10 kilowatts. And so we're doing industrial element checks and doing the agricultural yields. Most of the area is still going to be farmed conventionally, but all the ones that are kind of off the main farm field are going to be farm experiments that are going to run. Of all the experiments that we're doing, the kind of like A plus grade agrivoltaics is when you use the electricity from your agrivoltaic array to power indoor growing. And so that's what we're going to try here. This idea of the agri-tunnel with Food Security Structures Canada. You can do either partially buried tunnels, or this would be like the version you put out in the deep north. So you grow, say, something that you know is shaped like a raspberry on the outside. There's the electricity pushed on the inside, where you have these vertical grow walls. You get immense productivity per acre, and it can be climate control, and maybe even push electricity back onto the grid, but I'll tell you that after we finish this experiment. So we're literally building this right now. To do a lot of this work, we make all of our own electronics, we make all of our own monitoring systems, and one of the ones that we just came out with is the BREAD system. So it stands for Broadly Expandable and Reconfigurable Data Acquisition and Automation Device. After I said it once, just the BREAD, the rest of it's on. The idea here is to work where if you have a specific function you're interested in, you want to monitor temperature, you want to monitor density, we do a board just for that. And then these all click together, work on I2C, and work on software we've already developed. So you can make a more and more complicated system, and it literally is plugging it in, adding another module to the code, and just go. And so we've done very complicated things with this, pyrolysis systems, bioreactor control systems, and now we're expanding it to basically everything that Micro does. Some of which involve monitoring the crops. So one of our projects is using computer vision and machine learning to tell if strawberries are diseased or not, how big they are, so that we don't have to go out and measure them. To do that, this bottom screen with the computers is using Blender. Blender, I can't, like this next presentation is going to be quite useful for you. Blender is so powerful. You can't tell the difference between a Blender image and a real image. And what I've been using it for is to make Blender images of 3D printed parts. Then I train the machine learning with the 3D printed part, but because I've designed it, it's pixel perfect. So, you know, any of you that have done computer vision know the worst part about that, especially as a grad student, is you have to trace out a bunch of stupid pictures. They're like, this is 3D printed, this is not, this is a strawberry, this is a car. It's tedious, horrible, terrible work that your generation is doing after you graduate. You've all done everything and no one will have to do that again. And what I'm hoping to do is to supersede all of that. So instead of looking at 1,000 pictures of strawberries, figuring out what's a strawberry and what's not, instead you do the code for a strawberry. Then you use Blender to take the camera and spin it around. You take the background and change it to 20 different things. You have the code, of course, everything you do is parametric. So the strawberry is changing its shape, it's getting slightly diseased, it's bigger, it's smaller, it's got 5 leaves, 3 leaves, 2 leaves. You run that, let the computer chug on that all day long, your supercomputer cluster, which is running Linux. Then you take those images that you have the masks for, you train machine learning with it, and then you take it back to pictures. So I've done this with pictures of strawberries, and I've done the Blender thing with printers. We're just working on it now to do the Blender strawberry version. And if this works, this is going to change, at least for my group, how we do all of this type of work from now on. Instead of training images that we get off the internet or we take ourselves, forget that. That takes too long, and it involves people doing horrible work. Instead, we do one cool model, and let the computers do the rest of the work for us. On the agrivoltaic systems, we've developed our own racks, a whole big bunch of different kinds. And always what we're trying to do is to push the costs down to the point where the farmer, like a small scale farmer, not like a $1 million farmer, could build it him herself. But one of the cheapest racks we've got so far is the fence-based rack, which really isn't a rack at all. It's 4 metal zip ties. You take your module, you take a fence that you've already got, you zip tie it to it, you're done. We did the electronics for this and the mechanics for this, and every type of fence that currently exists on Canadian farms can handle at least 1 module per 2 upgrades that I'm showing here. If you're lucky, you might get 2 in. But regardless, the cost per watt to do 4 metal zip ties is nothing. Your labor cost is basically nothing. It is a very cheap way to go. But that's if you don't have a fence yet, and you want to put up your own fence. And that's what we're looking at, the top design. Now, the problem with this design is, and the reason that all racks are metal now, is that if you try to do a vertical billboard out of photovoltaic module, put in the highest wind speeds in Canada, you break the wood. And then you end up getting the thicker and thicker pieces of wood to the start to the point that it's just ridiculous. So what we've done is, instead of making it a flat billboard that just stays there, and put them on hinges so that they can swing when the wind blows. That kills the force that you're now applying to the modules. According to simulation, this would be absolutely no trouble. And one of the interesting things about this now is that we have simulation tools to do fixed tilt PV, and we have simulation tools to do fixed vertical tilt PV, but we didn't have when the wind blows, it changes its velocity. So we did that, and it turned out that we got a 12% gain. Now, this is just simulation. I don't know that it's really good. Theoreticians in the room will say, of course it's real. and you gotta make an experiment, do it, and we're doing that. So I'm hoping we get the 12% gain. If that turns out to be the right way to do things, all of our stuff is gonna be on just from here on out. But we'll see, hopefully next year. Okay. For putting solar panels on greenhouses, that's not an obvious thing to do because you shade the plants underneath. The whole idea of the greenhouse is sunlight to do it. Yes, you can power LED lights, but you're never going to win on efficiency that way. And so if you're going to try to have a solar powered greenhouse, one of the things that you need to do is have a partially transparent solar module. And if you could go a little bit better than that, you could also, and that's so the light is improved. And so there's a couple different companies that are doing specialty coatings or things that go into glass in order to make greenhouses more effective. And if you combine that with photovoltaics, you get even more output. It's to the point that you can start to think about running a heat pump to power your greenhouse instead of using natural gas. And so we're doing a lot of work with both experimenting and theoretically on the greenhouse front, and then taking that same idea and bringing it to the residential sector. We're already in Ontario today. It is economically viable for you to have a solar powered heat pump for your home. It beats natural gas, but your return is only 2 to 3%. As we were talking about earlier, nobody's going to get excited about that. It's a good thing to do, and if you haven't done it to your own house, you should consider it. But we need to go bigger and better. And the way to do that is to have some form of very low cost storage. And so we're banking on thermal batteries right now to be able to put us there. And again, we'll let you know. But one of the other super cheap ways that you can make a rack is to get rid of all the rack and just have your solar cells floating on water. Solar cells don't float on water, so you got to help them out a little bit. We tried to do this with foam. So I ran these experiments in Michigan. We got a winter's worth out of it, and it seemed to make sense. And I just redid them last winter on these little fake ponds. And what we showed is that the solar panels on foam will weather a Canadian winter, at least in London. It's not the worst Canadian winter, but it's at the beginning. And if you put a bubbler in it, you not only do the weather, but there's even no ice whatsoever. And so the cost of foam plus a little bit of marine glue is, again, nothing compared to a conventional rack. And so if you have a water system, even in Canada, you can reduce the water that's evaporating off your body of water. In places like Las Vegas, it pays for itself just on water savings. And so you get a huge big benefit there, but we're showing that it's useful for us here in Canada as well. Last but not least, some. Has anybody in here used Homer? So Homer is America's answer to microgrid software. I'm sure people don't know it. Yeah. It is pretty good. And I've used it in my group for years to look at like complicated systems. So if you want to couple like a cogen unit with PV, it's great. But if you want to do something new, like if you're taking data from Ottawa on bifacial module, and you want to stick it in a Homer, it doesn't work. It's not made for that. You can only do what they let you do. It's commercial software, it's closed source, you can't do anything. And so what we did is we made Sama to do everything Homer can do, at least in the PV space, and everything I wanted it to do. And you can too, because it's open source. If you have something that you're thinking about doing a microgrid with, and you have some new capabilities, some new modeling, you can couple it into this. And of all the things that we've added to it, one of the most important is we could do machine learning based predictive modeling. And so now you start to get way more complicated than what Homer's been able to do before. The first thing we threw it at was, should people disconnect from the grid in the US? The answer is yes. In way more places than you'd suspect, if you do an optimized system first. All right, so all the stuff that I talked about provides all of you with an opportunity. If you build equipment in your lab to test something experimentally, not only can you publish it conventionally and say actually photovoltaics, special conferences, or any of the normal solar energy and journals, you can also publish the hardware. And so I'm the head editor of HardwareX. And it only publishes open hardware, which means that you have to put an open source license on it in order to get it published, and you can get an article about your hardware that then other people can use to make more new conventional things. It's a gold open access thing, which I know probably some of you at least have a problem with it. I do. But if you're doing anything that relates to organization, which is pretty much everything in solar, I can give you a free APC waiver, which means you just publish it for free and life is good. Also, if you have crazy ideas and you want somebody, a partner, to try them out slightly crazier than you are, I'm happy to oblige. So we have a fully instrumented site. We're up for pilot testing anything. We have world
top class, I basically only accept the top 10% of my group, no matter what. We can try to leverage it for the other grants. If you are starting a company or thinking about starting a company, and if looking for future employees, and if you feel I might have some people for you. If you're looking for publishing partners and PR partners, I'm very much interested. And the one thing that's not in my group that we're leveraging pretty strongly is the biotron. So I think it's the largest, but it's pretty large regardless. Synthetic environments for agriculture and plant growth. So you can do things like have the entire top row of the building is different mini greenhouses. So you can have one greenhouse like Canada circa 2050, one Canada circa 2080, one 2100. And so if you want to see like change the carbon dioxide concentration, change the temperature, you can do that so you can predict what agriculture will be like in the future. And if you're interested in agrivoltaics, I happen to have a bunch of very interesting modules to play with. That if you're doing any type of work in that field, or you're making your own PV modules, or making new coatings for PV that have slightly different spectral characteristics, and you want to see if it would be any useful in agrivoltaics, I'm very, very interested. We can do a lot of fun things in the biotron with it. All right, so last couple things. Why should you do open source development? You will innovate faster. You will innovate faster because you'll have more friends doing it. You'll get more citations because of that, which will give you more exposure, which means that more companies will come knocking on your door. More students will send you emails asking to be a member of the group. It reduces costs. There's no question about that. So I started at Western 2.5 years ago. I've already expanded half of my own space. Like I'm now moving into other people's labs because I've filled it up with so much toys, because we can make toys for roughly a tenth of the cost of what it costs a normal person to buy. You'll have greater impact. You'll help more people. You'll get better students and employees. It's faster and easier to collaborate. You don't have to do NDAs. Don't have to talk to the lawyers. You just go. Students do their best work. And the reason I think this is because the student's name is all over it. So if you do secret lab work for some company, you earn your paycheck and you do good work, but that might not be your best. If your name is Bob and it has Bob's name all over it, it's going to be published on everything, every line of code. It had better be good because your name is Bob or whatever it is. You don't want to be known for the rest of time, especially in your own field, for things that aren't good. And so it encourages everyone to give their very best effort every time. You'll get free help. And so my group, I know, has benefited constantly for people all over the world, sending us improvements on our designs, giving us some ideas, correcting our wiki pages, like all kinds of good help. Because we share, you will get help. If from nobody else, at least me. What FAST can do for you? If you're doing something that might benefit from being solar powered, we're interested. If you're doing some kind of open source parametric 3D printable design, we can absolutely help with that. We have every 3D printer that you can think of that is open source. You can integrate your idea into the open source community, and we can kind of help lead you on. You're doing anything that involves open source computer vision or AI, we might be interested. If you're interested in pushing PV development faster in Canada, we're definitely interested. If you're doing anything that involves rapid prototyping, distributed manufacturing that might help out poor people throughout the world, we're certainly there to help you. And then, for example, if you're doing a board for something specific and you'd like us to add it to the third system, that's an easy collaboration, and we can help you along with that. And then your technique, tool, sensor, no matter what it is, can then be part of this bigger ecosystem that everybody can take advantage of. I offered something free. So I've written a couple books. For those of you that are young academics, very tempting to go with a conventional publisher. And the very first time I did that with the open source lab book, I went with a severe scientific publisher, and I got in the contract, because the whole idea was about free, that they would make the book free. But I was not sad enough to tell them how to do it. And so the way we chose to do it was every month they would put a new chapter up for free, and then take it down and put the next chapter up. So if you're patient, you waited for 2 years, you could read the whole book for free. That's not what I had meant to do. My second book, I went again with a conventional publisher, but I was not strong to get that clause put in the contract, and they tied it down. And my original thinking was that I wanted as many people to read it as possible. I'll let them do it. They can make it black and white, just make it cheap so it'll get into the hands of everybody. And it was okay, but none of you ever read it, I'm sure, and it died. Third book, Catch the Sun, published with an academic publisher. We maintained they could do anything they wanted with the hard copy version, sell it for as much as they wanted, but that digital version was mine. I'm not giving it away. Lonnie Grafman, who's the founder of Appropedia, the guy with long hair down in the lower left, was my co-author on this. And so we've been kind of tag teaming, kind of like James Bond and Q, where I'm the Q and he's the cool guy that goes out in the field. He's gone all over the world, built PV systems. And oftentimes we would kind of team up where I would do something crazy and then he would implement it and then we get it out in the community. So this book is about normal people using solar to solve their own problems, using very many times unconventional systems. So like the cover of the Spanish version has a fence, chain link thing over top the modules. And you're like, why would you do that? And don't get stoned.
That's the reason.
There is some of that. There's also to protect them from stones. And you're like, well, why would stones fall on something that's on the roof of the building? That's because people throw stones. And then why would they throw stones at the building? Because of the monkey. You want to know why? That's a problem in certain parts of the world. Book. So this book is completely free. English, Spanish, and French versions are already available. And each should be coming out this next year. Mandarin will be next. It has open source schematics on how to do everything. If you want to power something solar, it will tell you exactly how to do it using off-the-shelf stuff. And then if you're making something on your own, you can get a little bit more creative with it. So I will end here. Everything that my group does is free. Everything I've talked about, everything we've ever done, you can download and start to use immediately. That includes access to all of our articles, the literature reviews that you can